Gecko feet adhesives have been a source of inspiration for human innovation for a long time. Biomimetics, the imitation of systems that occur in nature, has emerged as a new field of science, influencing the creation of better human systems. Geckos' ability to climb and attach/detach their feet to surfaces within milliseconds has been a subject of interest for centuries. Gecko feet do not stick to surfaces unintentionally, and stay clean and don't require pressure to stick to surfaces. Unlike pressure-sensitive adhesives, which require pressure and tend to degrade quickly, collect dirt and particles and generally do not work underwater, the mechanism of adhesion in gecko feet is different. The German scientist Anton Hasse proposed that gecko feet implement intermolecular interactions to stick to surfaces. Later, electron microscopy showed that each gecko foot has several 100,000 hairs, known as setae, which split into smaller branches known as spatula. The flat faces of the spatula, oriented outwards, maximize the surface area that comes into contact with the surface. The spatula are made of keratin proteins, and research showed that van der Waals forces were primarily responsible for gecko adhesion. The goal of the proposed research is to customize gecko-inspired adhesive technologies for space applications in manipulation and mobility. The NASA 2015 Space Technology Roadmaps report highlights the need for advancements in technology areas 4.3.1, manipulator components and grappling, and 4.3.7, as well as 4.2.4, small body microgravity mobility. Gecko-inspired dry adhesives have been identified as a potential solution for attaching to objects in space, including solar panels, fuel tanks, and insulation blankets. They offer the advantage of attachment and detachment with low forces and flexible approach and departure compared to conventional mechanical grasping. The proposed work will focus on new micromachining techniques to create molds that allow for customization of gecko-inspired materials for various space mobility and manipulation applications. The research will also develop highly anisotropic versions of the adhesives, which are useful for adhesive mobile robots in microgravity. Gecko-inspired adhesives rely on van der Waals interactions to provide adhesion, which only works at nanometer length scales. Microstructuring the adhesive material, using fibers, mushroom tips, or other microscopic geometries, increases the area of contact and allows van der Waals forces to provide adhesion. The proposed research will have three primary areas of focus: manufacturing process development, sensing technology development, and testing in application-specific contexts. Collaboration with NASA will be essential throughout the project to address the unique challenges of the space environment. Potential applications of the technology include assisting free-flying robots like Astrobee with a wider range of functions and allowing external robots to grasp uncooperative targets. The natural stickiness of gecko feet has long inspired research, and a company called NanoGripTech has commercialized the technology with several products available. SetexDA is a dry adhesive tape for parts fixturing, hanging, and mounting. SetexXG offers higher friction performance, and SetexCF is a fastener that can adapt to various shapes. The products can be tailored to meet customer needs and are being considered for applications in medical, manufacturing, and sports apparel. Gecko-inspired adhesives have the potential to lift a human up glass walls and even catch space junk one day. The invention is exciting for biomechanists and researchers alike, and the possibilities are endless. The proposed research by Arul Suresh at Stanford University focuses on the development of gecko-inspired adhesive technologies for space applications in microgravity. The goal of the research is to customize these adhesives for manipulation and mobility, in line with the technology areas highlighted in the NASA 2015 Space Technology Roadmaps report. Several NASA initiatives require the ability of robots to control objects and move in microgravity environments, both on small robotic crafts and inside the International Space Station. The development of gecko-inspired adhesives, which use van der Waals forces to provide an adhesive force between the adhesive and substrate, has been identified as a promising solution for this purpose. These adhesives permit attachment and detachment with low forces and without highly constrained kinematics, making them ideal for microgravity environments. The proposed research will focus on the development of new micromachining techniques for creating molds for these adhesives, allowing them to be customized for different applications. The research will also include the development of highly anisotropic versions of these adhesives, which are useful for adhesive mobile robots. In addition, the research plan will include the development of associated sensing technologies and testing in specific application contexts. Gecko-inspired adhesives have been the subject of extensive research for several decades, with many researchers taking inspiration from the millions of microscopic hairs covering gecko feet and legs. One such research team at Stanford University has developed a serial micromachining process that allows the customization of these adhesives for different applications. The eventual applications of these technologies could include the use of free-flying assistive robots in a wider range of functions and the ability of external robots to grasp uncooperative targets. Companies such as NanoGripTech have also taken the science of gecko-inspired adhesives out of the lab and into the market, with new products offering enhanced grip and reusability. In the future, it is possible that these adhesives could even be used to climb glass walls or catch space junk, making them one of the most exciting developments in recent years. The proposed research will require close collaboration with NASA to ensure the technology is properly adapted to the unique challenges and risks presented by the space environment. Several NASA initiatives require the ability of robots to grasp and control objects in microgravity, whether on small robotic craft to grapple and deorbit space debris in LEO, or on internal free flyers in the ISS. External crawling or free-flying robots for spacecraft inspection would also benefit from improvements in adhesive grasping technologies. Gecko-inspired dry adhesives have been identified as a promising solution for attaching to objects in space, including solar panels, fuel tanks, insulation blankets, and other structures. In comparison to conventional mechanical grasping, they permit attachment and detachment with very low forces and without highly constrained kinematics for approach and departure. Moreover, space-qualified versions of the silicone rubber elastomeric materials used to create the fibrillar microstructures have been identified. The proposed work will focus on new micromachining techniques for creating molds that allow gecko-inspired materials to be customized for various space mobility and manipulation applications. The research will include development of highly anisotropic versions of the adhesives, which are particularly useful for adhesive mobile robots that can attach and crawl over various surfaces in microgravity. Gecko-inspired adhesives use van der Waals interactions to provide an adhesive force between the adhesive and a substrate. Van der Waals forces only work at nanometer length scales, so intimate conformation to the surface is essential. This is generally accomplished by microstructuring the adhesive material, using fibers, mushroom tips, wedges, or other microscopic geometries. In each case, the microscopic features greatly increase the true area of contact, allowing van der Waals forces to provide useful adhesion. The unique aspect of the techniques developed by myself and others at Stanford is the serial nature of the machining process. Accordingly, it is possible to vary feature geometries from mold to mold, and even across a single mold, which gives us the capability to tailor the adhesives for different space applications. The proposed research plan involves three primary areas of focus: development of the manufacturing process, development of associated sensing technologies, and testing in application-specific contexts. Close collaboration with NASA will be required through the entire project, as engineering an adhesive for space applications cannot proceed without knowledge of the unique challenges and risks the environment presents. Eventual applications of the technology could permit free-flying assistive robots such as Astro-B to perform a wider degree of functions, such as loading/unloading of automated cargo delivery flights. Gecko-inspired adhesives are also useful for external robots and grasping uncooperative targets. The natural stickiness of geckos' feet has inspired decades-long research efforts to develop advanced adhesives. Now a company spun out of a university research group called NanoGripTech has taken the science out of the lab and into the market, through a number of newly available products promised to deliver enhanced grip and reusability. Mechanical engineer Elliot Hawks of Stanford tested the new adhesive by strapping his feet to footholds connected to the patches through a rod. He found that he could easily peel off the patches one at a time and stick them to a wall with his hands, which was how the 70-kilogram PhD student ascended a glass wall behind his lab on a crisp December afternoon. At the end of the climb, he even let go of both his hands in a thumbs up while the patches stuck securely onto the wall, providing him with 2 secure footholds. Though he climbed only 3.6 meters, Hawk says the patches could work just fine carrying him up to the top of the Burj Khalifa, if he's not too tired of walking up 830 meters, that is. The Dubai sandstorm that nearly foiled crews in the movie would pose a problem, though, as the device works only on clean, smooth surfaces, Autumn says. But therein lies the beauty of the system. It could easily adapt to different situations, just by replacing the adhesive tiles with other types of gecko-like adhesives, for example, adhesives that self-clean like real gecko hairs. The team is now working with NASA's Jet Propulsion Laboratory to create adhesive-equipped robots that can catch space junk such as defunct satellites, Hawk says. In a recent experiment in a zero-G environment, a bot equipped with a small adhesive patch gripped the solar panel of another 400-kilogram robot, slowed it down, and gently pulled it in another direction. This is the future of bio-inspired design, Autumn says. It's not just about copying nature, but understanding it deeply enough to go beyond it.